And there was a tie for first between Maxwell's equations and Euler's equation. Euler's equation is this thing, e to the I pi plus 1 equals 0. And you can kind of see why, Euler's equation is so cool. It has in it everything. It has the 5 basic numbers, 0, 1, I, pi, and e. It has addition, multiplication, exponentiation, all in this very compact form. But for the same reason, my own choice would have been Maldaceno's equation. ADS equals CFT. Because it has everything in it too. It has Maxwell's equations in it, but it has non-abelian gauge theory. It has the Dirac equation. It has the Klein-Gordon equation. It has quantum mechanics. It has gravity. Pretty much has everything, that we know about the fundamental structures of nature, plus a bunch of other stuff that theorists have thought was a good idea, but we haven't seen yet, like supersymmetry and extra dimensions and string theory. And it's all in there in one sort of irreducible package. Okay, so I get to teach you about this. I've actually never given lectures about ADS-CFT before, so it's been a good chance to get my conventions and factors of 2 straight. I'm going to focus on, as Tom said, the main theme of the school, which is, well, to the extent that I focus on anything, the main theme of the school is using what we know about the left-hand side to learn more about the right-hand side. Of course, the other direction is ultimately probably even more interesting because this gives us what is right now our most precise construction of quantum gravity and non-perturbative string theory. So today I'll just talk about mostly generalities, motivation, and so on. Then the middle part will be just the basic, dictionary, the basic stuff you need to know, because the later lecturers will assume that you know it. And then I think in the last lecture or two, the thing I'd like to focus on is to talk about all the different ways that you can bang on this. Of course, that is break its symmetries in many ways, and get to, broader and broader examples of the duality. This is interesting, in particular for the applications, but also it's just an interesting subject. Okay. Good. So what I want to do first is a hand-waving derivation of this, which is not the way it was originally thought of, and it makes liberal use of hindsight. But it has a number of advantages. One of them is it gets you from this side to this side without actually going through string theory, which actually a lot of the applications seem to do as well. But it's a fun, it actually, along the way, illustrates a lot of the central ideas. So the hand-waving derivation is to start with the following idea. In gauge, so this is a connection between gauge theory and gravity. In gauge theory, we have spin 1 photons or gluons. And in gravity, we have the spin 2 graviton. And so wouldn't it be nice if we could make the graviton as a bound state of 2 gauge bosons? Now, this is one of those ideas which is so obvious that it's either very deep or very crazy. And in fact, it's probably both, because Weinberg and Witten have proven that it's impossible. So there's a famous no-go theorem due to Weinberg and Witten. And the essence of it is that when you get gravity, gravity is just not some massless, gravity is not just some spin 2 bound state that happens to be massless, because along with gravity, you get much more. You get the equivalence principle. You get coordinate invariance. And so in particular, it means that a theory of gravity has a lot fewer observables than a theory without it. Because in a theory without gravity, we can talk about expectation values of local operators and say where they are. But in a theory with gravity, since your space is fluctuating, and because even classically the coordinates aren't meaningful, it's much harder to define invariant observables. And so there's a much bigger conceptual difference between the two sides. And the essence of this proof was to consider an object. Here's the putative massless spin-2 bound state, the energy momentum tensor, which exists as a local operator in the gauge theory, and to show that if, in fact, you succeeded in this, this object would have impossible properties. And it's a great no-go theorem. It rules out a lot of things one might otherwise try. But in fact, most of the really great no-go theorems in our field turn out to have exceptions, to be wrong, and the exceptions turn out to be much more interesting than the original theorem. An example of this is the Coleman-Mendula theorem.
Question?
Yes, please.
So I just want to go back to your heuristic description of it. So on the gravity side, you say there are too few observables?
There are fewer observables. There are fewer observables, or fewer simple observables.
Okay, so
And this is always an issue in quantum gravity, because especially when you're in a place like de Sitter space where you don't even have a place to stand in some sense, right? There are fewer observables in gravity. Oh, sorry. Did you want to finish your question?
Yeah, I just kind of want to understand how you're counting observables.
For the present purpose, I'm counting them in the most naive sense. This is something which is meaningful in a Lorentz invariant non-gravitational theory because I know what I mean by X. But in order to tell you what I mean by X in a theory with gravity, I have to somehow, where is it sitting given that the space-time itself is dynamical. And you need to say, an attempt to define this will inevitably be non-local, because it will have to you'll have to sort of do some kind of geodesic transport, but that transport depends non-locally on the metric itself. Yeah. Anyway, the thing about these no-go theorems is, to prove a no-go theorem, you have to make an assumption about the framework for what the answer can look like. And you can list all of your assumptions to be very systematic, but always there are assumptions which are so obvious and trivial that you don't even mention them. And so Coleman and Mendula, many years earlier, found all possible symmetries of the S matrix. That was the title of their paper, more or less. And it was a no-go theorem because it ruled out something that a lot of people were trying. They were trying to combine the newly discovered SU3 flavor symmetry with SU2 spin into SU6. And Coleman and Mendula killed this whole activity by showing that you couldn't unify space-time and internal symmetries that you couldn't have a symmetry that combined the two. Now, and that was a great, again, it was great for ruling out a bunch of ideas, but they missed something important because they made an implicit assumption, which was more or less they assumed that the symmetry generators had to be bosonic. Actually, I looked back at the paper when I was preparing these lectures, and they didn't actually say those words. That assumption entered in a more subtle way, but essentially that assumption was made. And, of course, what they missed then was what Cyber is going to lecture about. They missed the possibility of supersymmetry. And so, again, at the time, it was obvious that generators were bosonic, and you didn't even think about it. And of course, had they listed that assumption and thought about it, they might have discovered supersymmetry. Anyway, the hidden assumption in Weinberg, and there may be more than one. There may be more ways to violate this theorem that you can't make gravity out of gauge theory than we know about, but the hidden assumption is that the graviton that you form moves in the same space-time as the gauge bosons out of which it's made, which again is a natural assumption. When you make hydrogen out of an electron and a proton, everybody moves in 3 dimensions. But again, with liberal use of hindsight, there's a clue that that shouldn't be true. There's the holographic principle, the observation, well, first of all, the observation of Bekenstein and Hawking that the entropy of a black hole is proportional to its area, but rather than its volume, as in normal statistical systems. But beyond that, if you have some volume, contained in some surface, a black hole is the thing that has the largest number of states by far that you can put in that volume. And so if you have a gravitating system, this suggests that that you should be able to describe all of its degrees of freedom by degrees of freedom living on the surface of the volume rather than the interior. So this is Tufts and Susskind's holographic principle. So the degrees of freedom that you're building gravity out of live in one less dimension than the gravitational theory. That's the clue. So if here you want 3 plus 1, over here you start with 2 plus 1. If you're interested on the gauge theory side in 3 plus 1, over here you get 4 plus 1, and so on. Okay, so so taking this clue, we'll go back and try to make this idea work. So again, here's a spin 1 particle. I'll call it a gluon. And here's another one. And they're in some kind of collective state. And somehow we're supposed to interpret this as living in one more dimension than the gluons themselves. Where is that going to come from? And one way to think about it is where this extra coordinate comes from is that it's the separation between the two, the size of this dipole state. You can, in fact, look, again, with hindsight, you can look at various parts of the phenomenology of QCD where you have gluon dipoles and where the separation of the gluons acts in many ways like a fifth coordinate, that specifically color transparency and the so-called BFKL formalism. By the way, if you don't get the acronym down, all of these notes will be handed out. Anyway, there are places in QCD where this separation acts much like a space-time coordinate in the sense that interactions are approximately local. Dipoles tend to interact most strongly with other dipoles of the same size. And also where, when you write down the wave function for this collective state, it actually looks 5-dimensional in the 4 center of mass coordinates and the separation. Yes? Z. Well, in principle, Z is not compact because the system Z can run from 0. So, in fact, Z will run from 0 to infinity until lecture 4. Yeah. Oh, because of confinement. Actually, we'll come. Sorry. Let me come back to that. Yeah. So, good. Okay. So, in fact, let me answer that question right now. So again, when you look at this gluon pair, you're saying to yourself, this is a graviton moving in again one more dimension, the center of mass coordinates, and the separation. Okay. So what I want to do now, so if this is true, what I want to do, what we can do very quickly is to figure out what is the shape of this 5-dimensional space. what is its metric. So I want to think actually not about QCD, but I want to start with scale invariant quantum field theories. And in fact, in the parts of QCD where this phenomenology works, QCD is approximately scale invariant, where those color transparency and BF. And since in some sense quantum field theory is nicest when you have the largest possible range of scales to look at, it's natural to start with scale invariant theories. And again, one of the things that I especially want to do in these lectures is talk about ways of breaking that symmetry, but that will again come only later after we understand the scale invariant case in great detail. So that means that, so here's a couple of my would-be gravitons interacting. And I want to imagine that the quantum field theory is, again, scale invariant. So if I scale up everything, I scale up both, okay, I'm going to try to scale up the whole picture uniformly, meaning both the center of mass coordinates of the pairs and also their separations. So whatever the space is that we get should be invariant under rescaling uniformly x to lambda x and z to lambda z. And if you write down the most general metric, that's invariant under the usual Poincare symmetries of space-time. Oh, actually, I have more Blackboard, don't I? Yes. Good, good. Well, I didn't really need Euler's equation again. So, if you write down the most general metric that's invariant under those two scalings, it is this, where you see, again, the Poincare symmetries realized here, and the scale invariance is guaranteed by having both the numerator and denominator quadratic. And actually, by a small order 1, it turns out, rescaling of the z coordinate, I can get rid of this prime and have only one length scale in the metric. So we get a metric which is fully determined by the symmetries up to its overall size, and this, of course, is anti-de Sitter space. If that z squared were a t squared, this would be de Sitter space, or a piece of it. Well, which of course is a good approximation to the current geometry of our universe. What's still very, striking is that although we can turn de Sitter and anti-de Sitter by this replacement in the metric, all of the ideas that we're talking about, we really don't understand how to continue them from anti-de Sitter space to de Sitter space. And in terms of the other direction for the duality, in terms of using the duality to construct quantum gravity, this is still, in some sense, this in some form is the biggest puzzle. It seems to really involve, new concepts and not just some analytic continuation. And again, it comes back to the question about observables, because in de Sitter space, in anti-de Sitter space, as we'll see, you have a convenient place to stand and look at the system and not have to worry about your coordinate system fluctuating. And in de Sitter space, we don't have that. So ADS space isn't expanding, it's warped. The normalization, there's a gravitational redshift on the 4 Poincare directions in terms of, or however many you have, in terms of z. And so if you're a local inertial observer carrying a clock around, which is running at a constant rate in its frame, it's running at different rates in terms of the x coordinates depending on where you are. The space is warped, and that's the key to, many of the aspects of the duality. Okay. So we'll, of course, say more about anti-de Sitter space, and we'll think about it in other ways as we go along. Now, to finish off deriving this duality, though, I need two more ingredients. The first, so again, there's a characteristic length scale here, and if we really want to talk about gravity as something which is, at least somewhat classical, so we can talk about a space-time metric, we need that the scale of the space be much larger than the Planck scale, which in terms of the black hole entropy, for the black hole, the Planck length is the basic size of the pixels on its surface, counting the number of degrees of freedom. And so what this means is that the largest black hole that we can fit in this space is pretty big in Planck units and has a large entropy. And therefore, we need that the dual gauge theory has a correspondingly large entropy. We need many fields. Specifically, well, at least the way it works in pretty much all the examples is some sort of large N SUN or some sort of large N gauge theory, large gauge group. The other thing we need is that we want that pair of spin 1 particles to look like a spin 2 particle, to look like a composite state, not to look like a pair of spin 1 particles, and so we need very strong coupling. And very strong coupling means not just coupling of order 1, but much, much greater than 1 in some sense. And as we go along, we'll say what we mean by very strong coupling. But I'll just mention, since that in terms of the examples, the basic examples, this generally means that the size of the ADS space is large compared to the string scale. Okay, good. Now, of course, actually, so I'd like to assert that, okay, this again was a lot of hindsight and plausibility arguments, but I'd like to assert that we've actually sort of gotten to the end. That is, if all of these things are true, if we have scale invariance, and if we have many fields and very strong coupling, and if we define those conditions sufficiently narrowly and precisely, then the claim is true, that the gauge boson pair acts like a graviton. And that's a safe thing to say, because because I said I could make the conditions, I left myself the freedom to define these conditions sufficiently narrowly and precisely. But I think that morally speaking, it's true. And I'll this very strong coupling in particular, I will quantify that in the next lecture or two in a different way. And then I'll come back to this point. But in some sense, under these conditions, it's true that the gauge theory will in fact behave like a theory of gravity in one more dimension. Now, these two conditions are also something one has to have in mind when thinking about the applications of this duality, because they control whether you have something which is really quantitatively precise, or whether you're simply getting a qualitative model of the system you want to study, a spherical cuprate. To play on Christian Observables describing ADS Rick physics as a spherical cow. Spherical cow, yes. Anyway, so if we look, for example, at the applications of heavy ion physics, the interesting thing is that the heavy ion collisions sit not at couplings much larger than 1, but at couplings of order 1. Couplings which are kind of midway between the perturbative description and where the gravitational description can work. And, well, sitting right between isn't so bad because you have a 50-50 chance to have the better description. And in fact, what we know is that for many aspects of heavy ion physics, the picture that you get from the strong coupling limit is better, closer than the picture you get from the weak coupling limit. But again, it's a qualitative thing. You're capturing the order 1 properties of the phase. Large N is, well, it's not clear how problematic it is. Clearly, these dualities are going to have some artifacts, some things that don't apply to the real world because N is large. But for the heavy ion, well, in the heavy ion physics, one way that you might sort of count the largeness of N is to say that the number of gluons is N squared minus 1. It's 8. And so your expansion parameter is 1 over 8, which is pretty good. But actually, if you count up all the quark flavors and colors, which aren't captured, but you're actually the effective value of N or N color over N flavor for heavy ion physics is of order 1. And so it's remarkable, in fact, that the duality works as well as it does there. And it's nice. It kind of shows that this large N limit it's fairly robust. It works at least qualitatively some ways beyond the range where it's quantitatively true. Now, for the condensed matter applications, again, the interesting systems have couplings of order 1, where if you can't understand them from weak coupling, strong coupling may give you new information. They don't really have large N. But again, in the past, condensed matter physicists haven't been above putting an N artificially into their problems to get an understanding of the phases of things. They work, in general, with large N vector models, rather than large N matrices, which is equivalent to what's called mean field theory. And this is also sort of a mean field theory, but it's much richer, and so it may not be such an obstacle to actually capturing the physics of interesting phases.
Question?
Yes.
So you say, or you alluded to that the number of flavors it comes in like in the denominator when you're counting?
Well, So for low-energy hadron physics, NF over N sub C is of order 1. And if you think about it in terms of world sheets, a quark loop tears a hole in the world sheet. And so in any case, in the duality as it's let me just say, in the duality as it's used, one works with the N equals 4 theory, where you have only adjoint fields. And the statement is that the number of degrees of freedom of the fundamental, when this is of order 1, the number of degrees of freedom of the fundamentals is of the same order as the number of degrees of freedom as the gluons. And so if they were behaving very differently from the gluons, then the thermodynamics and so on, the transport properties wouldn't be right, but they still are. One of the things I want to mention in the last few lectures actually is again coming back to cases where this thing is of order 1 and asking about how ADS-CFT is changed by that. But that will come much later.
Yes. About being in different phases then when you get to you can get to that little conformal window and stuff like that?
Well, yeah, a good question. Yes, certainly that's, well, that's an interesting point, which is that we do know, well, of course, we do know that the physics of gauge theories changes when this gets large enough, thanks to Tom, in fact. When this number becomes of order 4, we know the exact ratio isn't clear. Although that is actually only affecting the extreme infrared physics. It doesn't actually change the physics in the scale, say, where things are approximately scale invariant. Yeah. But in fact, well, yeah. Daniel.
So you sort of gone from the gravity to the field theory direction and tried to sort of motivate these two requirements.
Yes.
Let's say I wanted to go the other way. You probably wouldn't say that these two
Well, what I just said was if I define them sufficiently precisely, then I believe they're sufficient. In particular, very strong coupling will be defined in terms of the anomalous dimensions of operators. And the statement is that the conjecture is that if enough operators get very large anomalous dimensions, so your theory has only a relatively small set of low dimension operators, that it's sufficiently constrained that, in fact, it does have a gravity dual. This is something that Itze and I have been able to show in a sufficiently narrow context, but I believe it's more general than that.
So, for example, if you were to take n equals 4 super Yang Mills and dimensionally reduce it to 3 dimensions,
yes.
Is a three-dimensional field theory would satisfy these two, or would it satisfy the more precise version of that?
It does have a gravity dual, yeah.
It's a sort of 5-dimensional ADS.
Wait, sorry. Right, so you said, well, actually, this is again is a subject for later lectures, but if you take the n equals 4 theory and you compactify it, well, you've broken the scale invariance by the compactification length, but as you flow to low enough energies, you discover sufficiently low energies, you flow to a new conformal point, new fixed point, which is in fact has a gravity dual. So, I mean, if that was your question, it's robust against that particular way of banging on it. Okay, I haven't mentioned supersymmetry, but it sneaks in there in the following way. Continuum quantum field theories, if you try to continue them to very strong coupling, usually don't get there because they break down first. Once the coupling is of order 1, there is usually some mode where you can start producing pairs out of the vacuum and gain energy because the energetic cost of producing the pairs is offset by some negative potential energy. And so in order to have a quantum field theory where you can actually get to couplings which are not just of order 1, but much, much larger than 1, and which stays there over a wide range of scales, as we're assuming, if you really want this in a completely stable way, you almost certainly need supersymmetry. The secret of supersymmetry, of course, is that, roughly speaking, the Hamiltonian is the square of some information operator or sum of squares, and so the energy can't go negative. No matter how strong you make the coupling, the system can't break down too badly because there's a floor on the spectrum. And so in all of the precise examples, we have supersymmetry. You can start breaking the supersymmetry at low energy. You can try to break it at high energy. But that's where supersymmetry sneaks into the argument.
Well, I mean, there are orbitals which break SUSY completely because of the inheritance principle.
Right. But in fact, I believe that all of those are ultimately unstable. And so if you really try to take the continuum limit, your theory will disappear instantaneously. Now, it may be that there are exceptions, but Alan Adams. This was Gary Horowitz and Jacopo Borghero and I, looked at preciseness in a situation where you might have hoped that you would have broken the supersymmetry in a way that was still stable because there were no obvious tachyons, and there were still non-perturbative instabilities. And we shouldn't be too surprised because presumably, although Tom might disagree, our own vacuum is unstable because it's not supersymmetric and will someday disappear. And so, it's not so bad to live with a small amount of metastability. We also haven't mentioned strings, by the way. That was, again, one reason for doing this. It seems like if our interest was to construct a theory of quantum gravity, we've done very well because we've only taken ingredients that we know we have in nature, namely gauge theory, and just pushed it to a regime that a new regime, and we claim we get a theory of gravity out. This seems very good. It doesn't need all those strings and branes and things that you guys use. But of course, in all of the examples where this is realized that we understand, except maybe for some really degenerate ones, when you get gravity, you get everything else along with it. You get the strings and the branes and everything else, and it's not a surprise again because, after all, Tuff foresaw a lot of this stuff. He foresaw many years ago that due to the planar structure of large N gauge theories, which we'll say more about, at strong coupling, they look like sums over, roughly speaking, they look like sums over string world sheets. So in the cases where this is realized, the theories of gravity that we get locally in the bulk are always, the theories that we originally discovered by quantizing strings, or something related to them now by the web of dualities that we know, like M theory. Okay. So that's the hand-waving derivation. Now, the way it was originally, hit upon, more or less, which I'll go through more quickly, was let's consider a stack of n coincident D3 branes. And if we think about string perturbation theory, I've got some world sheet here. Each additional, so that's a string world sheet, each additional boundary on the stack brings in, first of all, a factor of the string coupling constant, because it's a string world sheet expansion. The Euler number is going up by 1, but there's n places it can land, what we used to call a Chan-Payton trace, and so the expansion factor is Gn. And so perturbation theory is good when this, not just G is small, but when Gn is much, much less than 1. Now there's something else, a black brane, which is three-dimensional, again, sitting in 10 dimensions, but it's black, it's got a horizon and a vector, entropy and so on. And what it has in common with the D3 branes is that they both carry, so a three-dimensional object in 10 dimensions is surrounded by a 5-sphere, and they both carry the same 5-form flux integrated over that 5-sphere. So they have the same charge. And the metric of this, which for now I'm just going to write down, you have to believe me, but later on we'll not derive it completely, but get some of its scaling properties. Separating the coordinates into the 3 + 1 dimensions transverse to the branes and tangent to the branes, parallel to the branes, and the 6 coordinates transverse. And r squared is the transverse distance, and h is this harmonic function. And I'll tell you what L is. Okay, so this is the metric of black 3 branes. And if you look, so if you look at it, the far away it becomes just flat, the 1 in H. But as you approach the branes, H is blowing up, and so something's happening at the origin of the coordinate system. But what's happening there is not so bad. And by the way, one of the things I'm going to do in the later lectures is talk about things other than D3 branes, but 3 branes are special in a number of ways, in particular because what happens as you go to r equals 0 isn't so bad if you if you go to small r, where the second term dominates the 1 in h, then you'll just get something you've seen already today. Sorry. Anti-de Sitter space. But an additional 5 sphere. Okay, actually this is not the coordinate system I used before. I used before z, which was the separation, and now r is L squared over z. I used to always think in terms of r, now I think in terms of z, but you should get used to both because, okay. So, okay. The metric, in fact, is not becoming singular as r goes to 0. The curvature, this is a homogeneous space. The curvature is constant as you go down to r equals 0. We'll talk in the next lecture more about how to think about r equals 0, but it's not at least a curvature singularity. Okay, and this L, here's Gn again, and so when Gn is much greater than 1, then the scale of this space is large compared to the string scale. And so these two objects, which carry the same flux, the descriptions are valid in complementary regions. The perturbative description at weak coupling, the geometric description at strong, large Gn, and of course they're the same object, just described in two different regimes. But this is not yet a duality. This is not yet a duality. It's just saying we have one theory, the same theory in both cases. It's the 2B string theory that has D3 branes. We have the 2B string theory, and it has these objects in it, and we use different approximations to describe those objects depending on where we are in parameter space. Of course, G is a field. G is the exponential of the dilaton. So we have the possibility to adiabatically continue between these two things, to take the black thing, make the coupling weaker, 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 and it no longer looks black, and we find out what it was made of. And this was the key to the way that Strominger and Vafa first counted the states of a black hole. It doesn't work in a quantitative way here because they don't have enough protection from supersymmetry. You need a black hole with a finite zero temperature entropy. But although it still teaches you something interesting, as we'll see. But anyway, you have the ability to continue between these two descriptions. So again, in this description, we have open strings stuck to the branes, as well as closed strings moving off the branes. In this description, the branes seem to be gone, and we just have the closed strings moving in the geometry. Now, is there another magic blackboard underneath? Nope. Nope. Okay. Actually, I want those pictures. This doesn't move up? No, it does. I'm going to... Okay, well...
Do you have a whiteboard?
No, whiteboard, let me think. Okay, so let's use the whiteboard and think about the low energy limits of the two pictures. So over here we go to low enough energy. We don't excite any of the massive string states. So here's D3, here's black 3. Low energy, we don't excite any of the string states. All we have left are the massless open string states, which are, of course, just they're the gauge field stuck to the branes and the collective coordinates for the motion of the branes. So we have the massless open strings, which is which is this again. It's n equals 4, d equals 4, un gauge theory. We also have massless closed strings sitting out away from the branes. So these fields live in 3 plus 1. Then there's the closed strings out in 9 plus 1. And over here, if we go to low energy, again we have the massless closed strings living away from the brane. But there is another set of low energy states, which is if you get close enough to r equals 0, you have an r squared here. The warp factor is the coefficient of that is getting very small, which means that in terms of the asymptotic measurement of energies, it doesn't matter how heavy the object is. It could be an excited string. It could be a brane. It could be anything. If it's close enough to the to r equals 0, it will be light. And so as we scale down to low energy, what we see is, first of all, the closed string states, but also sort of the r goes to 0 geometry, strings in the r goes to 0 geometry, which is this AdS5 times S5. Okay, and now the so first of all, in both pictures we have the massless closed strings, which we're going to ignore. They basically decouple at low energy. They move because they move in so many dimensions. Their couplings are irrelevant, classical at low energy, and we can ignore those fluctuations. In some sense, later on, we can imagine what it would happen if we added these back in. And this is one way to think about what the observables are in the system that we're going to talk about. But for now, we can use the fact they decouple and just think about these two sectors. And we're going to make...
Question?
Yes, please. At this point, in terms of states, I just mean So, no, I mean specifically things like propagating gravitons. Okay. But you asked about the back reaction. So in the black picture, the back reaction is it's that. But in fact, this term is linear in this small parameter, and so. When you do string perturbation theory about branes in flat space, the string perturbation theory builds up this factor for you. Yeah. So yeah, it's in well, yeah. So we're going to make if we make the innocent sounding assumption that going to low energy commutes with this adiabatic continuation, then we get a duality. Because then we go to low energy in the D3 brane picture, get the this field theory, this 3 plus 1 dimensional supersymmetry gauge theory, and go to strong coupling. And if the diagram commutes, then it means that the strong coupling physics of this gauge theory is string theory in ADS5 cross S5. So that's the derivation. It actually, of course, where it got its force, sort of got its force originally from the fact that people were following people were studying the dynamics of this, the dynamics of this. They were doing calculations in this theory. They were doing very different calculations in this theory, and those calculations were giving the same answers for various quantities. And so this argument explains why they were giving the same answers. It's because they're in the same system. Now, that's so slick, you might ask, how could this argument fail? Well, the most obvious thing that could happen is that if you take the gauge theory and you go to strong coupling, you might encounter a phase transition somewhere. And so you simply don't get to where you thought you were getting to. In this case, because we have a lot of supersymmetry, it's hard for that to happen because the ground state over here has zero energy. It can't be that some lower energy state comes along and takes over as we increase the coupling. You could imagine more subtle phase transitions, but with that large amount of symmetry, it's very hard to get a phase transition between here and here. Yes?
Before you go ahead, in that column on the left-hand side, shouldn't there be massive closed strings as well?
No, because it went to low energy. We went to low energy there. Yeah. Okay. Now, you can think about ways this could fail. You certainly can think about ways this could fail. For example, it could be that in the gauge theory, as you go to strong coupling, a large number of states, interacting states that were at relative, that were at high, come down to low energy. That new low energy, that states move to low energy, and so by the time you get to strong coupling, what you get is not just the degrees of freedom you thought you had, but a lot more degrees of freedom. Now these can't be supersymmetric states because for supersymmetric states we know what they're doing, and generally speaking, the non-supersymmetric states seem to stay at even higher energies. But you say this is not a derivation. You can even if you take as an axiom that these things exist and have the properties we think we have, they have. This is not a derivation. You can imagine ways this could fail, but as with many of the other weak, strong dualities we have, it's much harder to it's hard to imagine ways that it could fail, and the simplest assumption is that it's true. Now, when we get one of the things again for the later lectures, when I try to do this, we can try to repeat this exercise for other brane configurations, and in particular when we get to systems that are relevant for condensed matter physics, where you've got densities of things, you start breaking all the supersymmetries, and you have no protection against phase transitions. And in fact, one of the challenges is for attempts to construct condensed matter systems from first principle, from a top-down construction like this, is that they tend to get into the phase that you didn't want them to get into, and so. For just this reason. So we'll talk about that. So anyway, yes?
So in what you described, the duality comes in when we are looking at the near horizon jump.
Right.
Right. So it's like far away from the brain, it's again mass is close 9 plus 1 and close to the
Mm-hmm.
So does something interesting happen in the middle? Right?
Well,
Or can we think of other set of dualities that might set in?
Well, someday some clever person will figure out what is dual to the original flat space-time that the whole system sits in, the asymptotically flat space-time that the whole system sits in. and this will be a small piece of it. But it hasn't happened yet. So, but no, I mean, once you get into the transition region, you know, well, there's not, I don't have anything simple to say. I'm sorry? So, you know, one of the funny things is, where is open string field theory in this picture? Open string field theory is certainly describing all of the stuff over here, and in some sense, because of this funny way that open string field theory contains gravity, open string field theory, in some kind of implicit sense, contains everything. In fact, one of the, let me come back to that in a second, though, because it's relevant to something I'm going to say shortly. Okay. The other comment is, of course, this duality is very striking because on one side we have quantum field theory, something we sort of understand in principle due to Ken Wilson, and on this side we have string theory, gravity, something we don't, know what it is. There are other dualities, weak, strong coupling dualities between quantum field theories and between string theories. And there's this whole web of dualities. And even in cases where, in principle, we know how to define both sides, and where there's comparably strong evidence for a duality, we don't know how to derive it. And I won't come back to this, but this is just sitting there as a challenge. What is it that's wrong with our understanding, even of quantum field theory, that we can have this sharp fact that is almost certainly true, and yet we have no framework for deriving it? There are simple examples of field theory dualities, like the weak-strong duality of the Ising model and bosonization, and there are higher dimensional versions of the Ising model, where there's kind of a canonical way to turn the one picture into the other by, basically a duality, a change of variables in the path integral. But this direct method just gets nowhere when you get to the richer examples. And again, what is it that we're missing? So I have a few more things to say in today's lecture, but maybe this is a good point to assign you a homework problem. Okay. Here it is. There's actually two homework problems. The first homework problem is, it's obviously absurd to claim that a 4-dimensional quantum field theory could be the same as a 10-dimensional string theory. Prove that it's wrong. It's obviously absurd. Find counterexample. And of course, exercise 2 is to explain why your counterexample is wrong. Okay. Because this is something that pretty much everybody should do or does when they encounter this. And when I first heard about this, I had a lot of vague objections which came down to this question of open string field theory, because I thought I already knew how you made gravity out of open strings. You use open string field theory where, due to the world sheet dualities, you got closed string graviton poles when you summed over all of the open string states. And so how can you do it if you keep just the massless open string states? Okay, that was one of the answers I gave to number one. I have to think about I don't have a quick way to say why it's not really an argument. I'll give you other answers to problem one that I and other people have come up with, and they're later on in the lectures. But it's anyway. That's good. So, just to, I guess I got 15 minutes left, which gives me enough time to finish with the main ideas. Actually, just a small one. The duality is actually between SUN, not UN, the extra U1 corresponds to the collective motion of the branes, the motion of all of the branes together, and corresponding is a gauged field, which is its superpartner. And if you look at in the original black picture before taking any limits, where that degree of freedom lives is in fact in this transition region. So the black brane sort of has a flat bit and then a throat. This is the same picture drawn sort of from a different perspective. And if you ask where the U1 collective coordinate lives, it actually lives it's in this transition region between where the 1 and the R4 terms dominate. And so as you take the ADS limit, it moves out of sight. And so you get just SUN. I'm sorry? What U1 mode did you say? So I'm saying that when you take the low energy limit and you look on the geometric side only in the ADS5 region, you lose actually one of the, you lose that part of the gauge group. Yeah.
But it's actually, it seems a little non-trivial though, because moving from the 10-dimensional perspective, moving the brane beyond support the transformation, just a redundancy of description.
Well, no, it's not really a redundancy description because you can imagine ripples of this geometry. That's a physical excitation. You know, the entire black 3-brane rippling is a physical excitation, which again is it's what happens. It's the adiabatic continuation of the U1 mode. But if you ask, indeed, in the throat, it's really just a coordinate effect. The only place that it has actual local invariant curvature is sitting in the transition region. Yeah. There probably is more to say about the U1, but this is, I think, the basic reason why it's going. And this, actually, you don't have to sweat about this because we almost always use this duality in the extreme large N limit where we're dropping things of order 1 over n squared, which is what this is. But when you start calculating gravitational loops in the bulk, which is a 1 over n squared effect, then you're talking about something of the same order of this, and you have to think about whether it's more subtle than what I just told you. Okay, counting parameters, we have on the gauge theory side, we have the Yang-Mills coupling, and we have n, the size of the matrices. On the 2B side, we have G, the strain coupling constant, and we have n, which is again the number of flux. Now it's the number of flux units, but it's the same n. And the precise dictionary for the couplings is that G is G Yang-Mills squared. Actually, sorry, I've got the 4 pi's in my notes. Let me actually look at them. Yeah, G is G Yang-Mills squared over 4 pi, which implies, in fact, that the ADS length to the 4th is just the string scale, the string length squared, alpha prime, the string length to the 4th, alpha prime squared times lambda, where lambda is G Yang-Mills squared. N. So just putting in the 4 pi's from the solution and from standard D-braneology, the dimension of the string coupling is based to first order is the square, since this is a closed string coupling and that's an open string coupling, the dimensionless closed string coupling is the square of the Yang-Mills coupling. So we can list kinds of evidence for this. symmetries match. And I'll say more about many of these as we go along. Symmetries. We can identify the supersymmetric states, and there's a lot of them on both sides. We can calculate some supersymmetric correlators and find that they agree. What I really like about this, though, is it's not just a highly symmetric thing. You can bang on it. You can break the conformal symmetry. You can break the supersymmetry. And when you do that, you no longer have quantitative control. You can't do a calculation in both pictures and compare them numerically. But what happens is if you do something to the gauge theory in terms of breaking it, it's like you give enough you perturb it in a way so that you would expect that the gauge theory would confine instead of being conformal, or break a chiral symmetry. And then you look on the other side of the duality, the geometric side, you find that this is what happens, that the strongly coupled, that the geometric picture of the theory tells you, in fact, that the theory confines or breaks chiral symmetry or whatever. So it's robust against symmetry breakings. In a fairly technical and still somewhat narrow way, using secret higher symmetries, there's actually some ability to calculate some things exactly for all values of the coupling. So both sides seem to be integrable, and I think well, this is still a subject which uses a lot of conjecture and guesswork, but there's some evidence that one can really quantitatively carry things all the way from weak coupling to strong and see it matching. You can identify long string states, and again, this is relevant because, it's a theory of it's string theory. It's not just gravity. There's probably lots more that I'm not thinking of, but I'm just listing the ones that I like. There is some ability. So this duality is a conjecture, a prediction about what this gauge theory does at strong coupling. And we do have some other tools to understand strongly coupled gauge theories, lattice gauge theory, and something less well known but still somewhat useful, which is light cone diagonalization. And the error bars are large, but there are at least qualitatively some numerical tests, and these will get better in time. Finally, we can compare with experiment, and that's the applied bit. And of course, this really doesn't count as a test, because if the predictions of the duality don't match the experiment, you wouldn't say you've proven the duality is wrong, but rather you've misused the duality. But still, it's worth remembering, that every time we use this duality, if we keep our eyes open, we might see that it predicts something that's crazy, and therefore it must be wrong. So every time you use it, in some sense, you're also testing it. Okay. Is it? No, I started 5 minutes late.
Okay.
And amazingly, I'm exactly on target to finish section 1 of the notes. So the last 2 comments, 2.5 minutes each. So the first is, one, sometimes here it's stated that the evidence only supports some weak form of the conjecture. So the first thing to address is how strong is this duality? But the problem is, what do we mean by a weak form? There really isn't any clearly formulated weak form. Something one sometimes hears, maybe not so much anymore, is that this only captures the supergravity states in the ADS phase. That's certainly not true. There are many, many more states over here than just the supergravity states over here. And there are many states over here that we can identify as stringy. Moreover, again, the near horizon limit captures all of the stuff in the near horizon region, not just supergravity. So that's not a sensible weak form. You might conjecture that this is out only in the extreme large N limit, the planar limit. But again, that really doesn't make sense because the planar limit would be dual to classical tree level gravity, but neither of those by itself is a consistent theory. Both of them need loops. Gravity loops over here, non-planar graphs over here in order to be unitary. And to a large extent, unitarity determines the perturbation expansion. So at least order by order in 1 over n, this should be true. How about non-perturbatively in n, exactly in n? And in fact, well, there's a very obvious thing which we know. I mean, it seems trivial, but it's not. An exact statement in n, which is just the fact that n itself is an integer. Because when you do the 1 over n expansion, you're really treating 1 over n as a continuous variable. But in truth, it's a discrete variable with an accumulation point at 0. And on this side, it's an integer because it counts something, number of fields. And on this side, it's an integer because it counts something, the number of flux units. And so it's very hard to think of any version of this duality which is true, which is consistent with everything that we know, which isn't simply true in the strongest sense. Now, you can object that we actually don't have an independent, non-perturbative construction of the string side. And so when I say it's true in the strongest sense, what I mean is that everything we know about this side, all of the approximate descriptions we have and all of the dualities, everything we can connect it to the extent that we know about this side, we know a lot, it matches what we find from the other side. So the first is just the assertion that this is true in the strongest sense that one can imagine. And the last thing is just to notice that on each side of the duality, there are local symmetries. In the gauge theory, there's the SUN gauge invariance. In the string theory, there is coordinate variance. There's the local symmetry of gravity. And these two have nothing to do with each other. Neither is contained in the other. It's characteristic of dualities that they act only on the physical information. They only act on the invariant observables. And the fact that in this picture, it seems like we need this extra redundancy to make the description, and in this picture, we need a different extra redundancy to make the description are not things that are visible to the duality itself, which acts only on the physical information. Okay, so I've given you your homework problems. Tomorrow I'll say more about each side, and in lecture 3 I will bring them together again. Thank you.
I have a couple of information items. One is